Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the reverse biasing of the PN junction. Let's start. By the time you finish this lesson, you will learn the effect of reverse biasing on the depletion region with concentration of minority charge carriers under reverse biasing and the current flow mechanism under the reverse biasing. In the previous lecture, I explained that there is only two ways to bias a PN junction or a diode. I covered the forward biasing in the previous lecture. In this lecture, I explained the reverse biasing of a PN junction. A PN junction is reversely biased if the positive terminal of the external voltage source is connected to the N semiconductor and its negative terminal to the P semiconductor. As long as VD is 0, the PN junction is in the equilibrium and the minority charge carriers are uniformly distributed all across the device length. Under the reverse bias due to the external electrical field, the electrons as the majority charge carriers of the N semiconductor get attracted to the positive metallic contact and therefore their concentration around the junction significantly reduces. As a result, on the N side, a new realm of uncompensated ionized dopant atoms is created. This is equivalent to saying that the edge of the depletion region of the N semiconductor moves a bit toward the right. The conclusion is that the width of the depletion region increases on the N semiconductor side under reverse biasing. Now let's see what is going on the P side under the reverse bias. The left end of the P semiconductor is connected to the negative metallic contact. Of course, this metallic contact is full of free electrons. The P semiconductor is full of holes and the holes are hungry for electrons. What happens is that the free electrons from the negative metallic contact enter the P semiconductor to recombine with the holes. You might expect that the recombination of the free electrons to holes takes place in a region close to the metallic contact. However, due to the depletion region electric field and thermal excitation, free electrons are attracted to the edge of the depletion region and there they recombine with the holes. As a result of this recombination, a new realm of uncompensated ionized acceptor atoms is created. In other words, the edge of the depletion region in the P semiconductor moves towards the left. Therefore, the same as the P semiconductor, what I can say is that the width of the depletion region on the N semiconductor increases under the reverse bias. Since under the reverse biasing, the width of the depletion region increases, and therefore its electric field strength becomes more powerful, the diffusion process gets significantly weaker, and for a reverse voltage of a couple of kT, the diffusion current gets almost zero. As you already know, the diffusion current is due to the majority charge carrier concentrations. But what about the minority charge carriers? What happens to them? To answer this, I first focus on the P semiconductor. The minority charge carriers in the P semiconductor are free electrons. These free electrons are repelled from the negative metallic contact connected to the P semiconductor. When the free electrons are within the diffusion length LP, they are affected by the depletion region's electric field and they are sucked into the N semiconductor. To preserve the neutrality of the neutral region of the N semiconductor, once the sucked-in electron arrives in the neutral region of the N semiconductor, a free electron leaves the device on the other end of the device through the positive metallic contact. On the N side, the minority charge carriers are holes and similar to free electrons, they wander around. When a hole is within the diffusion length Ln, it is affected by the depletion region electric field and is sucked into the P semiconductor. Now the P semiconductor has one more hole in its neutral region. To preserve the neutrality of the P semiconductor neutral region, an electron from the negative metallic contact gets in the device and recombines with the hole. I hope you just realized that how the current just flew through the device under the reverse bias. Now let's take a look at the density of minority charge carriers under the reverse bias. Far from the depletion region, the minority charge carriers are intact and are MP0 and PN0. However, when we get closer to the edges of the depletion region, the concentration of the minority charge carriers exponentially reduced, and exactly at the edge, the concentration of charge carriers becomes zero. At the edges of the depletion region, the electric field is so intense that no minority charge carrier can stand there, and they are sucked in the other semiconductor. Here is a simple drawing of a PN junction which is reversely biased. As we have seen so far, the current flow through the device is due to the charge carriers holes and electrons. I plotted the minority charge carrier concentrations for a reversely biased PN junction, and now is the time to plot the current density diagrams across the device length. The yellow curve is the current density due to the holes, and the green diagram is the current density due to the free electrons. As these curves show, close to the metallic contacts, the majority charge carriers are responsible for conduction, and as we get closer to the depletion region, the minority charge carriers become responsible for electrical conductivity. In the depletion region, Jn and Jp become flat. This means that in the depletion region, no generation and recombination processes take place, and the hole and electrons just passed through the depletion region. Adding Jn and Jp gives us the device total current density, J. Since Jn and Jp are complementary, J becomes a flat line. In this lecture, I discussed the effect of reverse biasing on the depletion region with concentration of minority charge carriers under reverse biasing, and the current flow mechanism under the reverse biasing. In the next lecture, you are going to learn more about the current density and energy band diagrams of a PN junction. Thanks for joining this lecture of Peacademia.